The universe is far stranger than we imagine. Every time we think we have the answers, we realize we've been asking the wrong questions. To humans thousands of years ago, this planet was the entire universe. Until we looked a little further, saw the bigger picture, and realized just how insignificant we really are. For most of human history, we were certain about how the universe worked. Certain that everything revolved around the Earth. Certain that our galaxy was the entire universe. Certain that the universe was frozen in place. And every time, we were wrong. This is the story of the greatest paradigm shifts in human history. The moments when our understanding of the universe didn't just evolve, it collapsed entirely, forcing us to rethink everything we thought we knew. To understand the first great paradigm shift, you have to put yourself in the 17th century. For over 2 millennia, humans lived in a very comfortable, very small universe. They believed with absolute certainty that the Earth was the immovable anchor of reality, that their world stood still, fixed at the center of everything, and that the sun, the moon, the planets, the stars, everything revolved around it. This geocentric view of the universe was built over centuries and accepted without question. To suggest otherwise wasn't just controversial, it was heresy and it was dangerous. Until one man decided to look a little closer. In 1609, an Italian astronomer named Galileo used a telescope he had dramatically improved and pointed it towards the night sky. When he looked at Jupiter, he observed something odd. 4 tiny points of light sitting beside the planet. At first, they looked like distant stars, but as he observed them night after night, he realized they weren't background stars at all. He had discovered 4 moons: Ganymede, Callisto, Io, and Europa circling Jupiter. While the discovery in itself was remarkable, it carried a devastating implication, that not everything revolved around the Earth. The spell was broken and the illusion was shattered. In a single stroke, humanity was not the center of the universe. Rather, we were just one world among others. The reaction to this was immediate. The church called it heresy, scholars mocked it, and unfortunately for Galileo, the consequences were severe. He was tried for heresy, forced to publicly recant his findings to avoid execution, and was sentenced to lifelong house arrest, where he eventually went completely blind and died in 1642. But still, his discovery triggered a profound paradigm shift, and within decades, the old geocentric model quietly collapsed, and a new heliocentric model, where Earth and other planets orbit the Sun, is started to become the new truth. The universe had just gotten a little bigger, and humanity, for the first time, a little smaller. While this might have been the first time we were wrong about the universe, it would certainly not be the last. After Galileo, we spent the next 200 years mapping our cosmic backyard, the solar system. For a long time, the rules of discovery were simple. You build a bigger telescope, you point it to the night sky, and you find something new. You first observe and then you discover. Reality was strictly defined by what you could see. By the 18th century, Newton's laws of gravity were the ultimate rulebook of the cosmos. Everything perfectly obeyed the math. In 1781, famed astronomer William Herschel accidentally discovered Uranus while he was surveying the skies for faint, distant stars. As astronomers continued to observe the newly discovered planet over the following decades, they realized that something wasn't right. Its orbit didn't match the predictions, and it drifted ever so slightly from where it should have been, seemingly breaking the laws of physics. Astronomers faced a terrifying choice. Either Newton's laws were fundamentally wrong, or the map of our solar system was incomplete. Then, in 1846, a French mathematician, Urbain Le Verrier, chose to solve the mystery. But instead of using a telescope, he used a pen and paper. He surmised that the wobble in Uranus's orbit must be due to the gravitational influence of a large unseen body in its vicinity. And by using Newton's laws of gravity, he predicted the exact location of this object. When astronomers turned their telescopes to that exact spot, there it was, a new planet, Neptune, exactly where the math said it would be. This changed everything. For the first time, humanity didn't just observe the universe, we predicted it. Reality was no longer limited to what we could see. This wasn't just finding a new planet, it was proof that the entire universe follows precise mathematical laws. Laws powerful enough to reveal what the eye cannot see. And as it turns out, this lesson would become one of the most important tools in all of modern astronomy. Because the universe, it seems, hides a lot. In 1992, astronomers were listening to the rhythm of a pulsar, the rapidly spinning corpse of a massive star left behind after a violent supernova. In its signal, they found something impossible: planets. Pulsars are one of the most hostile environments in the universe. Intense radiation, extreme gravity, constant chaos. Yet they found 2 planets in its orbit. The very first worlds ever discovered outside of our solar system weren't orbiting a warm, life-giving sun. They were orbiting a graveyard, bathed in deadly radiation. For centuries, our entire understanding of the universe was built on a single example: our sun and the handful of planets orbiting it. For a long time, we didn't know if it was unique. But now we had proof that there were planets beyond our solar system, and if they could survive in the deadly embrace of a pulsar, then they definitely could exist around billions of sun-like stars in the universe. So astronomers began to search, and just 3 years later, in 1995, they found the first exoplanet orbiting a sun-like star. And it immediately shattered everything we thought we knew about how planets form. It was a gas giant, roughly half the mass of Jupiter, orbiting dangerously close to its star. So close that it completes one full orbit in just 4 days, something that takes our planet 365 days to do. All the while, its outer atmosphere is slowly stripped away by stellar radiation. A gas giant this close to a star simply should not exist, and yet there it was. Its discovery proved the existence of other solar systems and launched an entirely new field of astronomy. And with that, we built better tools like the Kepler Space Telescope, pointed them at more stars, and found more planets. Until we realized that planets are basically everywhere. Billions of stars with billions of planets. To this day, more than 6,000 confirmed exoplanets have been discovered, with thousands more candidate worlds awaiting confirmation. Some massive, some small, some scorching hot, others frozen in darkness, and some surprisingly familiar. rocky worlds orbiting in the sweet spot we call the habitable zone. For the first time, we went from asking, are there other worlds out there, to could there be life on those planets? By the early 20th century, humanity had come a long way. We had found our place within the solar system. We had learned to detect worlds we couldn't even see. And by observing the night sky, we had begun to understand that the Milky Way was a vast, rotating disk of stars held together by gravity. For centuries, the Milky Way wasn't just in the universe, it was the universe. An enormous collection of stars floating in an otherwise empty void. But there was one problem. Astronomers kept finding these strange, spiral-shaped, fuzzy smudges scattered across the night sky. These things were everywhere. They called them nebulae, Latin for clouds, and most assumed they were simply glowing clouds of gas drifting within the Milky Way. Then, in 1923, an astronomer named Edwin Hubble pointed the most powerful telescope on Earth at one of these spiraled nebulae and made a startling discovery. By measuring the brightness of individual stars within it, Hubble calculated that this nebula was far too distant to be inside the Milky Way. This wasn't a gas cloud, it was an entire galaxy, the Andromeda Galaxy, 2.5 million light years away. And then it dawned on us, all those other fuzzy spirals scattered across the sky? Every single one of them was a galaxy too, each one containing hundreds of billions of stars. The Milky Way wasn't the universe, it was just a grain of sand on an endless cosmic beach. In a single discovery, the universe didn't just get bigger, it exploded in scale. Today, we estimate there are more than 2 trillion galaxies in the observable universe. But as profound as this was, Hubble wasn't done yet, because in studying these distant galaxies, he noticed something that would shake the foundations of everything we knew about reality. Something that would take us all the way back to the very beginning of time. As Hubble continued to study the galaxies, he noticed something strange. The light from almost every single galaxy he observed was stretched, shifted towards the red end of the spectrum. And the further away a galaxy was, the more stretched its light appeared. In physics, this is called redshift, and there is only one thing that can explain this behavior: when the object emitting the light is moving away from the observer. Just like how the sound of an ambulance that fades as it speeds away from you, visible light shifts towards the red end of the spectrum because the light waves traveling through space are being stretched out. Except, in this case, the galaxies weren't simply flying away. Rather, the actual fabric of space-time itself was stretching, which meant the space between us and those galaxies was physically growing, carrying the galaxies along with it. This meant only one thing: the universe wasn't static, it was expanding. And in that moment, a terrifying realization emerged. If everything is moving away from everything else, then, in the past, everything must have been closer together. Rewind the clock, and the universe gets smaller. Rewind it billions of years, and the galaxies are on top of each other. Go back far enough, and all of space, matter, and energy must have been compressed into a single point. A singularity. The universe suddenly had a history, a beginning. Astronomers called this event the Big Bang. But for all of its elegance, the Big Bang remained a theory. a controversial, mathematically accurate theory with no direct proof. Until 1964, when a pair of radio astronomers named Arno Penzias and Robert Wilson picked up a persistent, annoying static signal while testing a giant radio antenna. They checked everything. They recalibrated their equipment. They even found a pair of pigeons nesting inside the antenna and chased them away, but the signal remained. What they had stumbled upon, entirely by accident, was the cosmic microwave background radiation, the faint, ancient afterglow of the Big Bang itself. Light from the very first moments of the universe is stretched and cooled over billions of years into a faint whisper of a microwave radiation, filling all of space in every direction equally. Penzias and Wilson won the Nobel Prize in Physics for their accidental discovery, and the Big Bang became the foundation of modern cosmology. We had finally traced reality back to its origin. But understanding how any of this was possible required a new set of scientific laws, and luckily for us, Einstein had already written them. For over 200 years, the universe was governed by Newton's laws of gravity. Gravity was a force, a simple, invisible pull between objects. It explained the motion of the planets, the fall of an apple, and it felt like the universe had finally been solved. But as our observations became more precise, we started to notice some oddities. Orbits that didn't quite match the predictions, light behaving in ways it shouldn't. The deeper we looked, the more the cracks started to appear. In 1915, a physicist named Albert Einstein proposed something radical. Gravity isn't a force. And space and time are not separate things. Rather, they are woven together into a single fabric called spacetime. The Earth doesn't orbit the Sun because it's tethered to it by gravity. Rather, the Sun is so massive, it curves spacetime around it. And the Earth is simply rolling along that curve. This was a complete rewrite of reality. The theory predicted that light would bend as it passed through curved spacetime. It also predicted that time is not the same everywhere. It runs slower near massive objects. The stronger the gravity, the slower time flows. And embedded within his equations were predictions so extreme that even Einstein struggled to believe them. Regions of space where gravity becomes so intense that not even light can escape. Called black holes. Einstein's equations were clear. In theory, if enough mass were compressed into a small enough space, the curvature of spacetime would become infinite. An object so dense that its escape velocity exceeded the speed of light itself. Nothing could escape it. Not matter, not radiation, not even light. At the time, this seemed far-fetched. Einstein himself argued that black holes could not exist in nature. For decades, black holes remained theoretical. In 1978, a French astrophysicist named Jean-Pierre Luminet created this, the first ever scientifically accurate simulation of a black hole. He created it using a room-sized mainframe computer. But because computers of that era could not render images, the machine produced only numerical data. He then manually translated those numbers into a visual by hand. Through the 80s and 90s, astronomers studying the center of our own Milky Way began noticing something strange. Stars near the very center of our galaxy were moving at extraordinary speeds in tight, rapid orbits around something invisible and incredibly massive. There was only one thing that it could be, but it was invisible to us. inferred only by the motion of its nearby stars. Just like Neptune, we could detect it without being able to see it. Then, in 2019, for the first time in history, humanity captured an image of a black hole at the center of a distant galaxy. A glowing ring of light surrounded by absolute darkness. A prediction made real. Then, in 2022, we imaged the black hole at the center of our own galaxy, an object 4 million times the mass of our Sun, sitting at 26,000 light years away from Earth. We were no longer imagining these objects, we were seeing them. Reality itself had confirmed the most extreme predictions of Einstein's theory. Today, it is widely accepted that almost every large galaxy has a supermassive black hole at its center. But even with all of this, the galaxies, the expansion, the Big Bang, Einstein's equation, the black holes, there was still something that didn't make sense. The universe, it seemed, had one more trick up its sleeve. When we examined the galaxies closely, they made even less sense. They didn't behave the way they should. Their spin was too fast. So fast that they should fly apart. But they don't. Something unseen was holding them together. According to everything we understood about gravity, stars at the outer edges of galaxy should orbit more slowly than stars near the center. Just like how the outer planets of our solar system move more slowly than the inner ones. The furthest from the mass, the weaker the gravity, the slower the orbit. But an astronomer named Vera Rubin discovered that stars at the outer edges of galaxies were moving just as fast as stars near the center. Galaxy after galaxy, every single one, the same impossible result. Either gravity worked differently than we thought, or there was something out there surrounding every galaxy, invisible and undetected, providing the extra gravitational mass needed to explain what she was seeing. We call it dark matter. We can't see it, we can't touch it, but we know it's there because of what it does. And that's not all. When we study the universe on the largest scales, we see something even stranger. The expansion of the universe is not slowing down. It's accelerating. Galaxies aren't just moving apart, they are speeding up, as if some invisible force woven into the fabric of space itself, is pushing everything away from everything else, growing stronger as the universe expands. We call it dark energy. Today, we estimate that dark matter and dark energy together make up about 95% of the universe. Let that settle in for a moment. We live in a universe where 95% of what exists is invisible, undetected, and unexplained. Everything else is just 5%. We set out to understand the universe and discovered we can barely see it. If we look closely at the history of astronomy, a pattern emerges. We think we understand how the universe works. We build better tools to study the universe. The old beliefs shatter, and a terrifying new reality takes its place. So the question becomes, what are we wrong about right now? Because today, we may be standing on the edge of the next great paradigm shift. Maybe it will come from Mars, possible signs of ancient life that may have existed millions of years ago. What if one day we discover that our entire universe exists inside a black hole, or that there are other universes beyond our own? The possibilities are endless. And if history has taught us anything, it's that the universe is always stranger than we expect. But that's all the time I have for today. If you made it this far, thank you. If you liked what you saw, then please consider liking and subscribing, and share your thoughts in the comments. And with that, I will take my leave. I will see you guys when I will see you guys.